everyone, Mark here with another example of that 313A exam question. So this question is regarding pressure enthalpy diagram. The question tells us that R410A at the pressure of 105 psig and quality of 10% enters the evaporator and exits the evaporator as saturated vapor. Compressor then raises the pressure of refrigerant to 335 psig. The first part of the question tells us to plot the cycle. So we need to convert 105 psig to psia, which will be 120 psia, and the intersection of 120 psia and the quality of 10% will be 0.1, which is the beginning of the evaporator. Then the question tells us that the refrigerant exits the evaporator as saturated vapor. Therefore, this is 0.2 and this is point where the refrigerant exits from the evaporator and enters the compressor. Now, compressor raises refrigerant pressure to 335 psig. So from 0.2 we have to go and find the pressure of 335 psig, which is 350 psia, and we know that because when the refrigerant goes through the compressor, its entropy remains constant. We have to follow this constant entropy line, and this will be 0.3. So from 0.2 to 0.3 is the compressor. The next thing that we have to find is where is the end of the condenser. 0.3 is the beginning of the condenser, and we have to find 0.4, which is somewhere around here. And we know that when the refrigerant goes through the metering device, its enthalpy remains constant. Therefore, if we extract a vertical line from 0.1, this will be the metering device and this will be 0.4. Now, the first part of the question asks for NRE, or net refrigeration effect. And net refrigeration effect is basically the heat that is picked up in the evaporator. Therefore, it's the difference between the enthalpy of 0.2 and enthalpy of 0.1. And enthalpy of 0.2 is 120 and enthalpy of 0.1 is 35. The difference is 85 BTU per pound. So refrigerant has picked up 85 BTU when it goes through the evaporator. Next part of the question is, what is HOC, or heat of compression? And HOC, or heat of compression, is the difference between enthalpy at 0.3 minus enthalpy at 0.2, and enthalpy at 0.3 is 133. So 133 minus 120 is 13 BTU. So this is the heat that is added by the compressor. The next part is asking for COP, or coefficient of performance, which is the efficiency of the cycle. And COP is the ratio of NRE divided by HOC. So 6.54 is the ratio of the cycle. And the next part asks for compression ratio, which is the discharge psig divided by psia divided by suction psia, and it is 2.91. Now, to make this question more interesting, I have added another part to that, and in the new part I have raised the suction pressure from 105 to 135 and lowered the discharge pressure from 335 to 295, and we want to see how this affects the efficiency or coefficient of performance of this cycle. Again, we plot the cycle, and this is 150, the suction pressure, and this is 0.6, which is the end of the evaporator and beginning of the compressor, and NRE in the new case will be H6 minus H5, which is 81 BTU. And heat of compression for the new cycle is H7 minus H6, which will be 9 BTU per pound. So coefficient of performance for the new case will be 81 divided by 9, NRE divided by new HOC, which is 9. And we see that we have a great increase in the efficiency of the system when we increase the suction pressure and lower the discharge pressure. And I can explain to you in detail why it happens. And the compression ratio in this second case, for this case, will be 310 divided by 150, which is 2.06. Compression ratio has decreased in the new case. Now, typically in air conditioning, compression ratio is from 2 to 5, and in refrigeration, compression ratio can be as high as 7.5. If you have any questions, you can reach me.